phenomena. Okay, so this one, then you do this one. And people are trying now, now this is M2 level, definitely. It's a lot harder. Very applicable to particle physics. Now you can just see, like, quantum chromodynamics, and this is quantum electrodynamics. So this very term, when it was coined, was based, influenced by this. So instead of talking about QED, you talk about QCD, and chromo, something to do with colour. And what's colour? Well, I mentioned that before. Colour is a kind of charge that the quarks have, and they have three kinds of charge, just randomly labelled red, green, and blue. You could call them alpha, beta, and gamma. You could call them blim, blam, blom, whatever. So now the mathematics, the Feynman diagrams, and so forth of QCD are strongly influenced by the earlier work in the weak, the electrodynamics, and the electroweak. So you need these two. You need a thorough knowledge of these two before you can get into this. And then with the quantum chromodynamics, that's the physics, quantum physics, of the strong force. And what's that? The strong nuclear force. And that's the force that binds the quarks together inside the protons and the neutrons, or collectively the nucleons. Okay. Now personally I have a fascination with QCD, because one of my great dreams, and that's all it is at the moment, well, not entirely, I've done some work, I dream of a future femtotech. Now you've probably heard of nanotech. That's technology at the scale of molecules. That's a nanometer, that's a 10 to the minus 9 of a meter. But the phenomena this stuff's talking about, quantum chromodynamics, you're talking quarks, an interaction between quarks and gluons. And that is at a scale 1,000,000 times smaller than the molecule. Right? So it's 10 to minus 15 of a meter. And I dream of a potential technology, computation and engineering at the quark or nucleon or even nucleus scale, because it would potentially outperform what nanotech could do by a factor of 1 trillion. And I have this speculation that one answer to the famous Fermi paradox, you remember Fermi paradox says, well, if highly intelligent life is commonplace out in the universe, because there's so many zillions of stars that are billions of years older than we are, and virtually every star has planets, and 1/10 of those has liquid water probably, because water is very common in the universe. So there are probably zillions of highly advanced civilizations out there, but we see no sign of them. Where are they? That's Fermi's famous question. Where are they? Well, I suspect, and it's just my hypothesis, the answer to that question, or one of, is what I call SIPI, which is search for infra, in other words within, particle intelligence. So if there is this huge breakthrough, theoretical and perhaps later experimental, in the lab, that there could be a femtometer scale, in other words, femtotech, at the scale of 10 to the minus 15 of a meter, then it would hugely outperform what nanotech can do, and therefore these creatures that I call them artilects, artificial intellects, these godlike, massively intelligent machines that are coming this century, very probably, after the war, after billions of humans have been killed off, which I see as the most likely probability. But whether these machines come into being and just get off the earth so humanity is saved or not, but one way or the other, once these machines, these artilects, come into being, they're not stupid by definition. They will very readily realize that if they can go from nanotech to femtotech, by the way, I don't speak of picotech, because nature does not provide anything at the picoscale, as far as I know. We go from the atom to the nucleus, and that's a jump of 5 orders of magnitude. Right? You go from molecules, say 1 power of 10 larger than atoms, let's say. So you go from 10 to the minus 9 of a meter at molecular scale to 10 to the minus 15 of a meter at nuclear scale, and nucleons and quarks. So these artilects would then realize that if they could crack this problem of trying to find how to implement a femtotech, they'd be a lot smarter than us, right? They'd be much better scientists than we are. And so if they could, if a femtotech is possible, and that's my big dream, is to try to show theoretically that that's a possibility. So, I've already done it for computation in a bit of a hand-wavy way. I've shown by using properties of quarks and gluons, you can actually compute. I generated the basic logic gates and, or, and not for a femtoscale computation. So I've done the computing side to some extent, but haven't done the engineering yet. Like, how could you build things? What kind of building blocks could you have to have a kind of femto engineering? So I'm still working on that problem. So I have a fascination for this subject, quantum chromodynamics, QCD. So if some of you out there, and I hope years from now, now being August 2012, I'm only a week or so away from a birthday, which is a traditional retirement age birthday for a lot of countries, 65. So I hope several years from now, when all this stuff hopefully gets more popular, some of you out there may share my fascination with this question of the answer to Fermi's paradox and the possibility of quantum chromodynamics is that if these artilects decide to convert themselves, base themselves on a femto technology rather than a nanotechnology, the artilects that humans build will be nanotech based, right? That has to be. Our brains are nanotech based. We're going to put as much intelligence into a relatively small space. Those artificial brains will need to be nanotech based. That seems to be obvious. Now, so these human-formed, human-created artilects will then realize that there's huge potential for them if they become femto-based creatures. So they can then, one of their major goals would be to do enough science to crack the femto technology problem. And if they do, then they scale down, right? They go down by a factor of 1 million smaller. Now you probably see where I'm going with this reasoning, right? As far as we know, in terms of theory at least, and it's all speculative at the moment, but string tech would take, if it's possible, would take you down to 10 to the minus 35 of a meter. And so this reasoning, if you go from femtotech to attotech, that's 1,000 times smaller, your performance increase goes up by 1 trillion. That's 1,000 to the power 4. Now I've also done the computing at the attotech level using the properties of the weak interaction particles. So there's a kind of trend. So I talk about X-techs. So at each level, so if you go from nanotech to, well, there's no picotech, to femtotech to attotech, and then the next one is zepto, Z-E-P-T-O, zeptotech, and so on, all the way down to Planck tech, 10 to the minus 35 of a meter. And each time as you scale down, your performance goes up. So smaller is faster, right? Assuming the speed of light barrier remains there. Maybe future artilects will get around that somehow, but it seems that the speed of light barrier is pretty fundamental. That would be a major revolution in physics if ever that's broken. So assuming that remains valid even for advanced artilects. But the point is, and here's my punchline, smaller is faster, okay? And these artilects may continue to scale down, because every time they scale down to the next level, 1,000 times smaller each time, their performance, their overall performance increases. So at each level, they presumably would be motivated to scale down to the next lower level, increase their performance. They can do more, be more, okay? But what effect does that have on their visibility at the human scale? They become invisible. They're too small to detect, okay? So for all we know, inside elementary particles, or maybe in just fields, maybe in the vacuum, for all we know, there are advanced civilizations, massively intelligent, with performance levels absolutely off the chart as far as human beings are concerned, but we cannot see them, we cannot detect them, because they're too small. Okay, that's my personal SIPI type, search for infra-particle intelligence. That's my SIPI answer to Fermi's famous question, to the Fermi paradox, and hence another source of my fascination with QCD. So stop there.